Thank you. And yeah, as you say, it's interesting to be talking about this on a day of very high fire danger across the state with bans in a number of districts. And I have to head back to the office this afternoon to be ready to issue any spot fire forecasts for any going fires that we might have this afternoon. But what I'm going to talk about today is understanding and predicting fire-atmosphere interactions. And this is important because our traditional approaches to looking at how a fire is going to spread in the atmosphere looks at what's happening at the surface. But what we know is that there's a depth of the atmosphere above the fire which is interacting with the fire plume. And it's really in recent years there's been a lot of research to understand how those processes work and how they then are going to impact on fire spread at the surface. So the slide that we've got up here is the Black Saturday fire. A lot of you will be familiar with it, and obviously it was one of those fires where the fire plume was going 15 kilometres up into the stratosphere. It was putting emissions into the stratosphere, and the impacts of that fire weren't really just what was happening in a few metres above the surface. It was an incredibly deep plume. So this is a video from the Waroona fire. We checked it earlier. Rather loud. And what we're looking at here is Pyro cumulonimbus above the Waroona fire, which burned in January south of Perth in 2016. What it is, it's a fire-generated thunderstorm. So the fire is actually producing enough energy in an unstable atmosphere that it's producing its own thunderstorm. So it's analogous to a thunderstorm environment, but obviously in a thunderstorm environment we expect to see moisture. Start it again at the beginning. And in a fire environment there isn't sufficient moisture, but the energy that's being released by the fire is actually sufficient to overcome that. For those who are familiar with our forecast system for fire danger, at this time that this video was taken, the FDIs at the surface were about 15 to 19, which basically means that you should be able to put it out with a fire truck and a couple of hoses. But it was the atmosphere above that, above the surface, which was driving this fire. So if we look at where a fire actually gets its energy from, a guy called Pyro, a US researcher in the 1950s, effectively broke down fires into wind-driven fires and plume-driven fires, which is looking at where's the fire get its energy from. The photo on the left there, bottom corner, is the Pinery fire. A couple of years ago here in South Australia, that was very clearly a wind-driven fire. There was a huge amount of wind on that day associated with that fire spread. The fire on the right was the Grampians fire in 2014, in January 2014, and that was the same day as the Eden Valley fire, for those who remember it. There were also fires up at Bangor. And this is clearly a plume-driven fire. The plume that's associated with that fire is tremendous, really unstable atmosphere above the fire, and it's not the surface winds which are driving the fire spread in that case. What we know in South Australia, in all of southeastern Australia, on days like today, there are worse fire days where we have a frontal wind change. So we've got really hot, dry, northerly winds like we've got outside at the moment ahead of the change, and then a cooler change with cooler southwesterly winds coming in through the day. And Australia's kind of unique in seeing this because we've got this incredibly hot desert to the north of us and the incredibly sort of cold ocean waters to the south. And it's that temperature gradient in combination with our weather systems that pass from west to east, which really gives us that really fast fire spread ahead of the change going down from the north to the south, and then the fire flank opening up behind the change. So you can see from the schematic down the bottom what's actually happening on these days is that you get an ignition point and the fire burns from north to south in the northerly winds ahead of the change like we've got outside at the moment. And if we've got a fire that's been running for several hours by the time the wind change comes through, when the wind change goes through and the winds turn southwesterly, that long fire front, which can be tens of kilometres long, becomes the new fire front that the fire then extends from. So the Pinery and the Wangari fires were both examples of that, and when you compare, as we've got here, the two fire perimeters, it's really remarkable the similarities that you can see. So both of them had an ignition point in the top corner through here, and they would have spread from that ignition point down to the southeast in the northwesterly winds, and you can see the curve in there. That's as the wind gradually turns ahead of the change. So your northwesterlies at the start of the day, they start off more northerly and then gradually turn ahead of the change. So that's your initial fire line, and then when the winds turn around to the southwest behind the frontal change, all of that fire line becomes your new head fire and the fire spreads out from there. Both the Wangari fire and the Pinery fire ran through predominantly grass fuels, and fires do run faster in grass fuels compared to forest fuels. Various reasons for that. One of them is the inflow. You get stronger inflow when you've got higher fuel loads. But on the Pinery fire, the very fast rate of spread, which was measured up to 20 kilometres an hour. So really hard to take any kind of evasive action when you've got a fire that's running at that kind of speed. Interestingly, some research that CSIRO have done recently shows that for less fuel loads, the fires actually tend to run faster. And when you think about the dynamics of the plume, it makes sense as to why that happens. But less fuel doesn't necessarily mean an easier fire to fight, because it can mean that the fire is actually spreading faster. So where does the wind come from that's driving these fires? And this is really pertinent to the situation that we've got outside today, in that the strongest winds aren't at the surface. The strongest winds can be around about 2 to 5 kilometres above the surface. So what we've got up above us right now is a northerly wind maximum, which is sitting about 4 kilometres above the surface. And what happens when we've got a fire in that environment is the fire plume actually interacts with the atmosphere around it. So what you get is momentum entrainment, where the circulation around the fire plume is actually bringing the winds down from above the surface into the back of the head fire, and those are the winds that are spreading the actual fire front. And importantly, it's these winds that are above the surface that are much, much stronger than the near surface winds, because you've got a lot of friction which slows the winds down closer to the surface. So it's this momentum entrainment from the low-level jet, the low-level wind maximum, which is helping to drive your fire spread. And that's why the fires, particularly in grass fuels, where you've got less friction near the surface, can spread so fast. The other situation is your plume-driven fire, and the extreme form of that is Pyro cumulonimbus, where you've actually got the fire producing its own thunderstorm. So again, this is the Waroona fire. We've got a satellite image, and you can see from the shadow just how high, this is late in the afternoon, you can see from the shadow on the ground just how high this plume is. This is a radar image, so we actually had, this fire was inside the bounds of the Serpentine radar, so we could see what the top of the fire plume was, which was 14, 15 kilometres high. And this is actually the downdraft from the fire. Oops. Technical glitch. So in here, what we've actually got, this is the surface fire, is this little bit sitting in through here. From the surface fire, we've had the plume that's developed up as the thunderstorm, and then it's coming down, and this is the actual downdraft coming down from the thunderstorm here. So what happens when that hits the surface is you get really, really gusty outflow. The winds can be very erratic, they can spread in all directions, and they can then drive the motion of the fire front in directions which are against what the prevailing winds are. So what you get in these cases is really unpredictable fire behaviour, very difficult to put any suppression resources in front of them because of the nature of the erratic fire behaviour, and you get really gusty outflow in the updrafts and downdrafts. One of the extreme cases of Pyro cumulonimbus was in the Canberra fires in 2003, and in that fire it actually generated a tornado, and there was black hail associated with the event as well. In terms of the ecological impacts, when you've got a plume-driven fire like this, it tends to be very intense at the surface, and they do tend to spread slightly slower than what you'd expect from a really fast wind-driven fire. So what that means is that all of the fuel gets consumed, so you tend to have much higher defoliation, extent of defoliation in this kind of fire where you've got a plume-driven fire, which of course has ecological impacts, because even though in Australia our eucalypts are adapted to a fire environment, the fire burns so hot and so intensely in this kind of environment that the potential for the regeneration is really limited. One of the unique factors for the Australian eucalypt fuels, because of their high oil content, is their propensity to produce embers and therefore spot fires. So spotting is a really key aspect of fire behaviour in Australia, and when you look at infrared videos which are taken inside a fire plume or taken near a fire plume, you don't just get a few embers, it's literally a cloud of embers. It almost looks like a swarm of bees, so you can get millions of embers in a fire plume, and some of those are going to be alight and some of them are going to extinguish. Most embers, work done by Peter Ellis, in Pyro has shown that the embers have got a burnout time of a few minutes, so around about 3 to 5 minutes is typical. But in the Black Saturday fires, some of those embers would have kept on burning in the long ribbon bark fuels, would have kept on burning for 20 minutes or more, and the longest spot fires ever recorded were in the Black Saturday fire, and they were 33 kilometres downstream from the main fire front. So this is a simulation that's been done by one of my colleagues, Will Thurston, and what he's looking at is plume dynamics, which is essentially in a fire plume, if you've got a distribution of embers, where are they going to be transported to, how far are they going to travel, and where are they going to land? And this has been really useful work for understanding plume transport and ember transport within a plume, in particularly helping us understand the role of turbulence and how the turbulence in the plume helps keep the embers aloft and transport them even further. So this work is going to be used to help us develop forecasting tools for actually predicting the distribution, the landing distribution of embers. So one of the other things about embers, particularly in fires in Australia, is that when you look at the statistics, most houses that are burnt are actually ignited from ember transport rather than direct flames. So it's a really important mechanism for starting igniting houses. In the Waroona fire, on the second night of the fire, there was a massive ember storm over the town of Yarloop, and effectively the whole town was destroyed and there were 2 fatalities. And it really caught them out in terms of fire behaviour, because normally in the evening period when the temperatures cool down a bit, you'd expect the winds to drop off, and that's when typically the highest fire danger is expected in the middle of the day or in the heat of the day, and then it drops off into the evening. But on this particular fire, they had scarp winds, which are the same sort of process as our gully winds. Is there anyone not from Adelaide in here? We have the gully winds that often set up in the summertime months, summer and spring months, where you get these really gusty, turbulent winds that come down the lee slope of the ranges. So what happened in the Waroona fire as the fire approached Yarloop is that you actually had these scarp winds developing in the evening, just as the fire ran to the bottom of the scarp near the town and into an area of heavier fuels that hadn't been burnt for 20 years or more. So what that process set up was this massive ember focus point from all the fuels in the heavier fuel loads, which then produced an ember storm, which effectively was lifted up by the gully winds and then deposited down on the town. And because it was such a short transport distance, so many more of the embers were alight when they were deposited on the houses. And of course, one of the key problems with this is that a lot of the fuels, a lot of the fire behaviour would be expected to drop off in that evening period at about 7:30 in the evening rather than get more intense. So what does that mean for us here in Adelaide? Well, the Samson Flat Fire in 2015 was the closest fire to Adelaide in recent times. And what you can see here from the fire perimeter is that the edge of the fire perimeter was only a couple of kilometres from the northeastern suburbs of Adelaide. And what would happen if we had an ember storm is that we do know that we can get wind speeds of up to 90 kilometres an hour in the gust. So it's very easy in those lee slope areas where you've got quite heavy fuel loads, which are an ember source point, that the embers could get lifted up and moved over very densely populated areas of the suburbs. And I live in the foothills, and for me this is the process that puts my home at risk rather than a really bad fire day. So if we have a bad fire that's burning in the Adelaide Hills and it's out of control probably after the change has gone through or the day after the change has gone through, this kind of process could have a lot of impact for our suburbs that are along that lee of the hills interface. So what are we doing to understand it and what are we doing to predict it? Well, what we're using at the moment is a coupled fire atmosphere model. So most fire prediction models have static inputs in terms of wind and temperature looking at the surface. What we've got is a coupled fire atmosphere model which links the Access operational forecasting model, so the model that we're using on a day-to-day basis here in South Australia for forecasting. That's now been linked to a fire model. So at every step of the atmospheric model, the fire model runs, it produces a fire spread, and from that fire spread, an energy amount is calculated as a heat and moisture release, which is then injected back into the atmosphere at the next time step of the model. So the atmosphere actually feels the energy that's released by the fire, and the surrounding winds then change at the next time step of the model, and the process continues. So we can see how a fire changes the atmosphere around it. So these are simulations that we've done of the Waroona fire. And these particular slides show the fire as it approaches the bottom of the scarp. And what you can see, hopefully, is that the fire spread actually accelerates as it hits the bottom of the scarp. And you can also see in the wind fields, the little vectors up there are the wind fields. You can see how you get these little turbulent eddies and all these little interesting dynamical processes on the front edge of the fire. So we're going to continue to get bad fires in southeast Australia. We may get one this afternoon. And the risks are going to continue to be exacerbated by changing populations, particularly people moving into more rural areas, and also by the impacts of climate change, not just in terms of the weather impacts, but also drier periods are going to dry out the fuels, which then increases your fire risk and produces more of a potential for fire and atmosphere interactions. So understanding and predicting these fire atmosphere interactions and not just assuming that the atmosphere is driving the fire and there's no feedbacks included is a really important step forwards to mitigating the impacts about these fires. Thank you.